Welcome to our Mechatronics project. We started this project a few weeks ago because I remember some advice I received from a very wise man one day at about 9:30 in the morning. He said something to the effect of, make sure you start your project early because if you don't, you'll want to kill yourself. Luckily, it was a success. We're able to hit all the requirements. Unfortunately, this video only contains me and not my team members. My team members are busy doing some of Professor Hollis's Vehicle Design 2 and Mech Systems 2 work. So for the Mechatronics hand project, this is the presentation. For our project, we had a 3-finger design. It's got 3 fingers, 2 mechanically coupled by a gear and 1 thumb controlled by a servo. We've mounted the IR detector on the end of the thumb so that we can control it. And if we're not the most accurate at moving the gantry, we can use the thumb to compensate. The coupled 2-finger pinching motion here, that is shown by, or that's driven by the small DC motor with an encoder. We've added a PID controller and of course signal conditioning on the IR sensor as the rubric required. It's battery powered. It uses a 2-cell LiPo that I really do need to storage charge. It's been fully charged for about a week now as I worked on this. We have 3 layers of perf board. The first layer is the teensy, the battery eliminator circuit that makes a 2-cell high volt battery, so it's just over 8 volts, makes it into 5 volts. We also have our little motor driver from Pololu, and that connects nicely to our motor. The second level, we have these long dangly antennas that go to an FSIA6B. It's a 4-in-1 protocol radio receiver, and we have a voltage divider connected to it because the teensy's logic is 3.3 volts out, but all of the radio transmitters that I had are 5 volt out. So I had to give 5 volts to the radio receiver, and then on the signal pin, which is PWM out, I had to make that 3.3 with the voltage divider, and then that goes into the teensy so I don't fry it. The uppermost level is a resistor circuit for some LEDs that essentially just conditions the signal from the IR receiver per the rubric, and then some LEDs to let us know which one is coming up next. So I'm going to explain a little bit how our hand works, but so you don't get bored just watching me ramble, I'm going to play our demonstration video from the day of over it so you can see the video and listen. I'm sure if you're grading this video, you don't want to watch me go for a while, so you can at least see something moderately entertaining while I speak. So our project uses a teensy microcontroller to run a robotic finger mechanism driven by a DC motor. It has an encoder for feedback, plus an IR receiver and a signal conditioning circuit. The code is organized to satisfy the assignment requirements, which are using a DC motor instead of a simple hobby servo, using a closed loop control with an encoder, and using an IR sensor with analog signal conditioning whose output is processed by the microcontroller. At a high level, the program does 3 main things. It automatically homes the finger to find the mechanical limits and define a neutral position. It controls the finger and thumb based on an RC input using the encoder and a PID loop for the DC motor. It reads the IR receiver output as a frequency and uses 3 LEDs to show which IR distance band we're in. One requirement of the assignment was to use a DC motor with feedback, not just a servo. Because the DC motor on its own has no built-in position control, we pair it with an encoder on the finger joint. The encoder tells us how many counts the shaft has turned and in which direction, so the teensy can treat it like a position sensor. One of my favorite features of this design is the radio controllability due to the radio receiver we've placed on it. This obviously is under 250 grams, but luckily we got the okay on that one. So when it starts, it's got the homing sequence, which it does to find the zeros. And then now you're free to control it with one stick direction being for the thumb and the other being for closing and opening, also allowing for fine control to grab halfway, all the way, of course, for all digits. For the RC control, we did a mapping of stick inputs to the hand motion. For user input, the system uses an iBus RC receiver, so the hand can be controlled from a standard radio transmitter. One channel is assigned to the fingers, and another channel is assigned to the thumb, although over iBus it's just the same wire, so we only had to make one voltage divider. For the code, it reads the channel values, which are pulse widths from about 1,000 to 2,000 microseconds. We added a small deadband in the center to prevent jitter from the mechanical devices and the springs in the radio. For the thumb, the channel is mapped directly to the servo angle between thumb out of the way and thumb in pinch position. So for the fingers, the channel value is mapped to a desired position between the homed open limit and the homed closed limit, with a neutral point in the middle. That desired position goes into the PID controller, which drives the DC motor to make the encoder match the target. This gives the operator continuous proportional control. Small stick movements make small finger movements, and large stick movements drive toward fully open or fully closed. This homing is important because it lets the system know the absolute positions. For example, fully open, neutral, and fully closed, even though the encoder itself is only relative. We've also got some stall detection. We have current-based stalls and encoder-based stalls. Because we're using a DC motor and real hardware, it's possible for the mechanism to jam or hit something unexpectedly. To protect both the motor and the mechanical parts, the code implements two different types of stall detection. For current-based stall detection, the motor driver provides a current sense signal, which was built into the motor driver we purchased. The Teensy reads this as an analog value and filters it. If the motor is being commanded to move by the user and the current stays above a threshold for a certain amount of time, the code interprets that as the motor pushing too hard but not turning freely. Basically a stall or hard contact. This is useful when something physically blocks the finger, even if the encoder might still be jittering a little bit. We also have encoder-based stall detection. During homing and other non-RC phases, RC phasing meaning when it's in control from the RC controller or me, the code also looks at how much the encoder position changes over time. If the motor is commanded to move, but the encoder count barely changes over a certain window, that suggests the mechanism isn't actually moving, even though we're attempting to drive it. That's a second indication of a stall. So using both approaches gives a more robust protection. The current detects when the motor is working too hard, and encoder motion detects when there's almost no actual movement. In the main RC control state, the encoder-based stall detection is relaxed to avoid false positives during light load situations like grabbing objects, but current-based stall detection is always available as a safety net, especially because we smelled something burning during one of our tests. So when a stall is detected, the code stops the motor, reports it over serial, and requires the operator to bring the control input back towards the center before resuming. That behavior shows that the system is aware of abnormal conditions and responds within a controlled and predictable way. For the PID control, we have the PID position control for the DC motor. One of the other requirements was to show real control logic on the DC motor. Once homing is done, the main finger position is controlled by a PID loop using the encoder feedback. The code takes a desired position computed from the RC input and compares it to the current encoder reading. The difference is the position error. The PID controller uses a proportional term that scales with the position error, providing the main push towards the target, a derivative term that depends on how fast the error is changing, helping to damp the oscillations. Right now the integral term is just over 0, but if we achieved more steady state error, we would have increased it. The structure is still there to expand on. The PID output determines two things: how fast we drive the motor, the PWM level, and in which direction. The code also includes a deadband around 0 to reduce the noise and avoid motor chatter when the finger is close enough to the target. This is what turns the DC motor and encoder, something that behaves more like a controllable servo. The finger smoothly tracks the position command instead of just slamming into one end. So luckily we're able to hit all of the targets. Our hand worked on the day, and even though there was a slight burning smell the day before during our practice demonstration, did smell it again during, and Dr. Clark seemed very happy with our progress. We were too, so thank you to Dr. Clark. We had a great time demonstrating it, not a great time staying up late building it, but I guess that is how Mechatronics goes. So thank you so much for watching. One final thing, all of the wiring diagrams that weren't previously included in this video are going to be right here. Some things not mentioned in the wiring diagram, like exactly what pins go to what on the Teensy, are going to be in the code at the very top where we declare our variables, as well as some notes. I'm also going to attach a zip file with this video that contains our code and our CAD files. So if you're a student in Mechatronics 2 after I've taken it and you're watching this video because Dr. Clark said you gotta find a project and rebuild it, good luck with mine. Hopefully you actually have the zip file and not just this video, because if you don't, it's gonna be a lot harder. Thank you again for watching and have a wonderful time.